Hi guys, thanks for watching. In this video we're going to take a look at two questions. One being there's a connection between spontaneity as indicated by delta G and equilibrium as indicated by K. We'll see what that is. We're also going to answer the question why some reactions that are thermodynamically favorable still don't actually ever happen. Also remember that I'm making this video for a bunch of the people that won't be in class on the day the lesson is taught. So I'm going to start off the video the same day we would start off that lesson in class, and that's with a review problem of some of the topics covered the previous day. So if you want to give yourself that experience, feel free to pause the video now while you try to solve these yourself. And then as you click play again, you can see me go over the correct answers. Alright, hopefully you've had some time to attempt this problem yourself if you want to. I'm going to click into the answers now and go over those really fast. The first question asked if the reaction was thermodynamically favorable under standard conditions. So all you really have to do there is plug in all the values into the delta H minus T delta S equation. You come up with positive 431 kilojoules per mole. The positive value tells you that this reaction will not be spontaneous. Part B asked what sort of temperature change could cause it to be spontaneous. If you look at these two numbers side by side right here, you'll see that the T delta S term just has to get bigger than the delta H terms, which tells you that temperature needs to be increased until the value of that T delta S term becomes larger than the 490.7. It also asks you to identify this as enthalpy or entropy driven. Since the enthalpy and entropy values were both positive, we call that an entropy driven process. And finally, it asks you to solve for the exact temperature when the reaction becomes spontaneous. So plugging in 0 for delta G and solving for T, we come up with 2479 Kelvin. Okay, let's get straight into the first question for this video, which is, what is the connection between free energy and equilibrium? First of all, let's just remind ourselves that it should come as no surprise that there is one. Way back several lessons ago, when I first gave the definition for a spontaneous reaction, it even said right there that these are reactions that occur on their own in the direction of equilibrium. So you've seen this mentioned before. Let's start off by listing out the two possible signs for delta G, negative or positive, and remind ourselves that a negative delta G means the reaction is spontaneous as written. And if you think about that, spontaneous as written, all we're really saying is that that reaction happens. It turns its reactants into products. In other words, products are formed. So it should be no surprise to connect that to equilibrium and then say, okay, so that's a reaction that's product favored. And then if you think back a couple units ago, we know product favored reactions have KEQ values greater than 1, indicating there's more products present than reactants. At the same time, a positive delta G, which we know means it's not spontaneous, all that means is that the reaction doesn't happen as written. In other words, products aren't formed, which means they stay as reactants. So it should be no surprise that these reactions can be assumed to be reactant favored and have KEQ values less than 1. So here's an example of how you would use something like this. I have here the reaction of water turning into hydrogen and oxygen. Its delta G value happens to be positive, which means it's not spontaneous as written. We now know that you could also say this is a reactant favored reaction. The cool part is, if you flip it around to the reverse reaction, the sign for delta G switches just like you would expect for an enthalpy or any other thermodynamic property. Now that it's negative 240, that means the reaction is spontaneous now that you've written it a different way. The second reaction we could also now say is product favored with a K value greater than 1. Now besides this kind of conceptual link between spontaneity and equilibrium, there's a mathematical side too. One of the equations given to you down at the very bottom of your AP chemistry equation sheet shows you that delta G is equal to negative R, the gas constant, T temperature, times the natural log of K. This equation allows you to calculate back and forth between values of delta G and equilibrium constant K. Let's take a look at an example problem so you can see exactly how this equation is used. This question gives you a reaction down here that's been balanced. Gibbs free energies of formation for each species in the reaction, and it asks you to do two things. One, calculate a delta G, and then use that to calculate the equilibrium constant at 25 degrees Celsius. So let's handle the first thing on that list, which is use those free energies of formation to solve for the delta G of the reaction. That's simply our classic products minus reactants equation. Plug in the products, plug in the reactant values, which is nice and easy because it's both 0, and you come up with the free energy change for this reaction as negative 16.37. Once you have that value, now you can go ahead and use the negative RT ln K to solve for the equilibrium constant K. So here's the equation. First thing I plug in is the delta G. You'll notice one key difference. I changed it from kilojoules to joules per mole. You'll see why that is when you plug in the R value as 8.314. This is the R value we use because it has units of joules per mole Kelvin, so there's the energy connection we need in joules. Because the R value is in joules, that's why I went ahead and changed the free energy change to joules as well, so the units match. The temperature was 25 degrees, which is 298 Kelvin, and you just solve for the value K. Simplifying all those numbers, you come out with 6.6 equals ln K. And to get rid of the natural log, you do e to the power of 6.6, and the equation is simplified to a K value equal to 740. Also notice that this is greater than 1, indicating a product-favored reaction, which we expected anyways because the delta G value initially was negative. Let's finally move on to address the one other question we'll take a look at in this video, which is how come some spontaneous reactions don't actually happen spontaneously? In class we talked about a match burning or a piece of paper lighting on fire as spontaneous, and yet matches and all the paper in the world aren't spontaneously combusting. And the reason is that just because something is thermodynamically favorable and theoretically spontaneous doesn't mean it can't be stopped from happening by what really is the kinetics of the reaction. It's been a while since we've talked about kinetics, so as a quick refresher, here's a good example of what we're talking about. Carbon in the form of diamonds turns into carbon in the form of graphite with a delta G equal to -3. The negative value tells us this should be happening. All the diamond that exists in the world should be spontaneously turning into graphite. Clearly that's not happening. And the reason it's not happening is because diamond, as you might remember, has some of the strongest bonds. All the covalent bonds within the structure are so strong that the activation energy to actually start this reaction is so extremely high. We can see that on this graph here. The activation energy to start it is so high that the reaction really never even gets started. The way you would word this is that this reaction is thermodynamically favorable but kinetically unfavorable. And that pretty much wraps up the final video, the final topics of Unit 10. Hopefully you guys found it helpful. Thanks for watching.